Okay, welcome back. This is 10.2. We're dealing with rational exponents now. And, what are we talking about? Well, basically, for example, you're used to dealing with things like, I don't know, 3 raised to maybe the fourth power. That's equal to 3, 3 times 3 times 3 times 3. What is that, 81? 9, 27, 81, yeah, okay. Now, instead of having a nice counting number up in the exponent or an integer value, and so you could have negatives, we've dealt with negatives as well. Maybe we should try a negative, right? 3 to the negative 2. That's the same as 1 all over 3 to the 2. And then that's 1 all over 3 times 3 is 9. Okay, so we've dealt with integer exponents. Now we want to deal with fractional exponents. So you can have fractions up there. And at this point in our studies, it's not exactly clear what something like 3 to the 2/3 power would be. Okay. So what we need to do is talk about it, and we can in some cases simplify it, and we'll be looking at that right here. Okay. Okay, so first we'll start with the definition. Right? The definition of a to the 1 all over n. So we're only going to worry about it first, having something with a numerator of 1 in our fractions. Okay, so if the nth root, and I have to go to the technical definition in the book, if the nth root of a is a real number, and n is greater than or equal to 2, is an integer, then we can rewrite a to the 1 all over n using roots. So that's why we're throwing this in your lap right now. We can rewrite it as the nth root of a. All right, so of course, if n is even, we can't have a negative in there, and so there's kind of like little details written out in our definition. Okay. Right, so use radical notation. To rewrite and simplify. Yeah, I'm sort of thinking about it. This doesn't really say that they can't be negatives and we can't have the even root of a negative. This doesn't really say it. It's just saying that the a value that you're putting in here has to be a real number, and the n value here has to be an integer value. So integers are the counting numbers or negative counting numbers, so it could be a negative. But it's also, there's the assumptions that a is if n is even, then a is not negative. I think that's in the book. I didn't write it out though. Okay, so just be aware that the book has the good definitions, and a lot of times when I write my definitions, I'm just kind of worried about timing and boring people to death. So there's my definition. You want a better one, go to the book. Okay, so anyways, use radical notation to rewrite and simplify. Finally, let's do some homework. Number 2, I have 100 to the 1/2 power. Okay, so before that would have been kind of mystical. What is that? What's that fraction up there? But now we can see it as a root. Okay, so I put the 100 inside the root, and the 2 would normally go here. But because we don't ever really write square roots with a 2 there, we kind of aren't going to put it there in that case. So the square root of 100 then is just 10. Let's look at 6. I have negative 81 to the 1/2. you have to kind of remember what's the base and what's the exponent. So there, I'm sure back when you were first introduced to this idea, there were questions like, please note that -2 to the fourth power is not the same as -2 to the fourth. Okay? In this case, the base is just the 2. Okay? This negative here isn't attached to the 2. So really it's -1 times 2 to the fourth. Up here, though, the base is all of -2. So the 4 affects this -2. It's similar to saying 3x squared, right? You're not going to think that the 3 is affected by the 2 and say, ooh, this must be 9x squared because I have to square the 3. No, that's craziness, right? The base with regards to this exponent is the x. That's the base part. That's the part that's attached to the exponent. So this would be like 3 times x squared, and okay. So that's what I was getting at. Hopefully you've seen that before. So here it's really -1 times 81 to the 1/2, and we could rewrite that as -1 times the square root of 81. Okay, and then that'll be -1 times square root of 81 is 9, so that's -9. So get one more. Here's number 10. So I have 3xy to the fourth raised to the 1/5. Okay, this time everything is in the base of the exponent, and so we're going to have to put all of this inside of the root. Okay, so the 5th power means we have a 5th root, and then we put the 3xy to the fourth inside of there. Okay, so in the beginning, you're just dealing with a 1 in the numerator, and then we change that, right? We want to deal with all rational numbers. So section 2 then, we look at that phenomenon. The definition of a to the m over n. So m as in, I don't know, machine, and n as in nanofiber. M over n. Where are we? So the deal is you can kind of separate a fraction. Like for example, if I had 3/4, I could rewrite 3/4 as 3 times 1/4. Okay? You know, why can I do that? Well, look, 3 is the same as 3/1. And then if you multiply 3 times 1, you get 3. And then 1 times 4, you get 4. Okay? So we can kind of pull these fractions apart and pretend that whatever our exponent given to us is, we can rewrite it kind of in a new way. So if I have 8 to the 3/2, I could also write that as 8 to the 1/2 times 3. In other words, I could write it as 8 to the 1/2 then raised to the 3rd power. Okay. And maybe then on top of this, you need the reminder of the exponent rules. If you have a base raised to a power raised to another power, to simplify, you multiply the exponents, right? So this would be a to the 35. If you have bases multiplied by each other, a third times a to the fourth, and they have the same base, then you add the exponents, excuse me. So the case we're looking at is this first case. Okay. But we're going kind of in the other direction. I have a to the 35, and then I know that a to the 35 is the same as a to the 5 times 7, right? So I could write it a to the 5th to the 7th, and really if you go in the other direction now, 7 times 5 will give you 35. So up here, that's what I'm getting at. Okay? If I have 8 to the 3/2, that's the same as writing 8 to the 1/2 times 3 because of this baloney. And then finally, I can rewrite it using our rules of exponents as 8 to the 1/2 and then parentheses 3rd. because if you re-multiplied these exponents, you would get 3 over 1 times 1 over 2, which would be 3 times 1, which is 3, and then 1 times 2, which is 2. You get back to where you started. Okay. Okay. There's some technicalities, with the definition. I'll leave that reading to you, but in general, there's going to be all these little technicalities, but in general, if you have a to the m all over n, that's going to equal a to the 1 all over n raised to the mth power, which then you could rewrite as a root. You could say that's the nth root of a raised to the mth power. And this is going to give us a powerful way of simplifying these expressions and making new expressions. Likewise, if you can do it that way, you can kind of do it the other way, right? You could say this is the same as a to the m raised to the 1 over n. And so you'll have the nth root of a to the m. Okay? And those are considered equivalent given some conditions. Okay? But in general, this will hold. And let's take a look. Let's take a look at some problems. Okay, so here's number 12. We have 25 to the 3 halves. Okay, so I want to rewrite it in a way that will allow me to simplify it in my head, basically, is my sort of understanding of why we do these. I don't want to use a calculator to type all this in, right? So you have 25 to the 1 halves raised to the 3rd power. 25 to the 1 halves is the square root of 25, and that's cubed. Square root of 25 is 5, and then 5 cubed is 125. Okay. Let's look at 16. We have negative 27 to the 2/3. Okay. So I'm going to rewrite it as negative 27 to the 1/3 and then squared. So I have, 1/3 there. So I have the cube root of negative 27 squared. The cube root of negative 27 is negative 3. And I want to square that. And then negative 3 squared is 9. Okay. Let's look at some other ones. And the directions here in the book are to rewrite with rational exponents. Okay. So here we have 24, the cube root of 6. Okay. So I'm kind of now going in the other direction. This will be 6 to the 1/3. So I get 28. I have the square root of x to the 5th. So I can rewrite that as x to the 5th to the 1/2. And then I can multiply out the exponents, and that would be x to the 5 halves. Let's try 32. So I have the 7th root of x to the 4th. So that's the same as x to the 4th to the 1/7. And then if you multiply out your exponents, if you forgot, you consider 4 is the same as 4 over 1, and then multiply straight across. So you get x to the 4 times 1 all over 7 times 1, x to the 4/7. One more, 36. We have the 6th root of 9x squared y. We're raising this to the 5th power. Okay, so this will be 9x squared y to the 1 over 6, and then raised to the 5th. And then we multiply out the exponents, and that gives us 9x squared y to the 5/6. You can see that, there it is. Okay, okay, so the next step then, we're looking at rational exponents. So you have to include negatives in that set of exponents, and that's what we want to deal with here. So section 3, basically negatives in your exponents. If you have then a to the negative m over n, that's going to be the same as 1 all over a to the m over n. If you look back in your book or in your notes from your previous classes, you'll see that's the general rule for negative exponents. You just kind of put it in the denominator and change the sign of the exponent. So let's look at some of these. Here's, what is this, 44. We have 81 to the negative 5/4. Okay. So ultimately, if possible, we want to simplify. So first off, this is 1 all over 81 to the 5/4. Then I could rewrite this by kind of factoring the exponent into 1/4 raised to the 5th. The 4th root of 81 is 3. And then finally, 3 to the 5th power is 243. If you multiply it out, 3 times 3 times 3 times 3 times 3, you get 243. Okay. Let's look at 48. So here I have 8 all over 125 raised to the negative 1/3. So depending on how your previous teachers have taught you to do this, there may be more than one way. What I teach students is to just flip the fraction and change the sign of the exponent. Then we can take the cube root of this thing. Both of those numbers are perfect cubes. So 5 times 5 times 5 is 125. 2 times 2 times 2 is 8. Sorry, so this is a 2. 5 halves is our answer. Let's look at 50. We have negative 8, the base, negative 8 raised to the negative 2/3 power. Right, so I'm going to take the negative 8, drop it to the denominator, and change the sign of the exponent. Then I'm going to rewrite it. So it's negative 8 to the 1/3 power and then squared. So basically I have to take the cube root of negative 8 and then square it. So the cube root of negative 8 is negative 2. And then square negative 2, and that's just 4. So you end up with 1/4. Let's try 54. 7xz to the negative 1/4. So the only number affected by the negative 1/4, the base of that is right here. It's the z part. So when I rewrite it, you can either automatically drop it to the denominator, or you can write it like this. It's kind of a reminder of how things are working. And then multiply it out. So 7x is still the same as 7x over 1, and you get 7x times 1 is 7x all over 1 times z to the 1/4. Okay. Generally, I just like to go from here to here, but it's up to you. Okay, so now we kind of want to put it all together with the general rules of exponents. So first off, we'll probably have to remind you of all those rules. It seems like every time I take a new math class, I have to go through and rememorize these rules. Well, I mean, not anymore, but when I was a student, that's what I have to do. I have to open up the book and make sure I remember these rules. They're so important. So what am I talking about? Well, the first one, if you have the same base in the denominator, like you're trying to multiply a cubed times a to the fourth, you have to add the exponents. So it'd be a to the 3 plus 4, which is 7. Okay, so I'm just going to show you examples. In the book, they'll give you a bunch of generalized statements with variables. If you have something like x to the fifth all over x cubed, and you want to simplify that, you can bring the way you think of it is bringing up the x cubed. It's really, though, a subtraction, right? So here, when I multiply, I add. Here, when I divide, I subtract. So you end up with x to the 5 minus 3. Okay? But sometimes you need to go in the other direction to keep things, you want to end up with something positive, right? So x to the 5 minus 3 is really x to the 2. But in other examples, so let's put like a big bar here for another example, you may have something like x to the fourth all over x to the seventh, right? And you don't want to bring the x to the seventh up and go x to the 4 minus 7 because you get a negative. Right, so what you do instead then is bring the x to the fourth down, and you get 1 all over x to the 7 minus 4. Okay, so you get 1 all over x cubed. So the point is you can bring this up and have, you know, this guy minus whatever the bottom is, or you could bring this guy down and you have this guy minus whatever that exponent is. Thirdly, we were just playing with this rule. If you have something like x cubed and you raise it to the second power, that's x to not the fifth, but the sixth. So always you got to remind yourself, this one's multiply. Okay, this one is add. Multiply exponents, add exponents. A product raised to a power. So if we have something like 3x squared y raised to the third power, you kind of have to go through and raise the individual factors to the third power. So this will be 3 to the third, x to the 3 times 2, which is 6, and then y to the third. And of course, we can simplify 3 cubed as 27, x to the 6, y cubed. The last one is quotient to a power. So it's pretty much the same idea as this, except you have a fraction. So let's try 2x squared y all over z. And we raise it to a power, let's say 4. So basically, you just have to go through and raise every individual factor to that power of 4. So you have 2 to the fourth, x to the 4 times 2 is 8, y to the fourth, all over z to the fourth. Okay. And then you can simplify this by multiplying out 2 to the fourth. 2 times 2 is 4, so is a 16, x to the 8th, y to the 4th, all over z to the 4th. Okay, so those are the main rules. You may have learned 1 or 2 extra variations, but those will get you through any problem. So when you're working with exponential expressions, we kind of have a simplification protocol that we want to follow. Like, for instance, you always want to get rid of negative exponents. Okay? What are some other kind of rules? You want to end up without parentheses. So eliminate parentheses. You want to eliminate powers to powers. You don't want repeated bases floating about, so it's basically a matter of combining like terms, except with multiplication instead of addition. So bases can only occur once. And then eliminate negative exponents, which is probably the rule you remember the best. Eliminate negative exponents, okay? All right, so let's take a look here. We got 56, 5 to the 2/3 times 5 to the 1/3. Okay? So we have a repeated base. We need to basically multiply these out, and you have the addition rule for multiplication of exponents. So you add 2/3 plus 1/3. Okay, so 2 plus 1 all over 3 is 3 over 3. And then you can simplify that fraction in the exponent. It's just 3 over 3 is 1. So you just end up with 5. That's kind of neat. Let's look at 62. I have x to the 3/7 all over x to the 1/7. Okay? So if you multiply exponents, you're adding. If you multiply two terms, you're adding exponents. If you divide terms, you're subtracting exponents. You want to avoid a negative. So you don't want to bring this guy down, because it would be 1/7 minus 3/7. You want to bring this guy up. Okay, so the exponent, the new exponent would be 3/7 minus 1/7, which would be 2/7. Let's try 66. I have 3 to the 4/5 and then raised to the 5th power. So in this scenario, you want to multiply the exponents. So you end up with, if we pretend 5, same as 5 over 1. You go straight across, you get 20/5, which is 4. Okay? And then 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay. 2 more examples and we'll move on to something else. There's a 68. We have y to the negative 3/4, then raised to the 1/6. So you have to multiply your exponents. So I have negative 3 all over 24. And then I want to simplify that exponent, y to the negative 1/8. And then I can't leave negative exponents floating about. So I need to take this and kind of move it downstairs. 1 over y to the 8th power. 1 over 8. Okay, so 74, what do we have? X to the 1/4 times y to the negative 2/5, and then raised to the 1/3 power. Okay, so I'm going to multiply out the exponents to get x to the 1/4, y to the negative 2/15. And of course, I hate negative exponents. I need to get rid of this negative exponent issue. So you can drop that thing to the denominator and have y to the positive 2/15. Okay, there's one more topic in this section. We're getting towards the end now. Section 5, using rational exponents to simplify. Okay. And the problem type, they want you to simplify and then put it back into radical notation. Okay, so simplify by converting to rational exponents, and then end with a radical of some sort. Okay, simplify and end in radical notation. Okay, so here we go. Number 80, I got the 10th root of x squared. 11 there. So I'm going to convert it to a rational exponent. So the root part always goes in the denominator. This will go into the numerator, have x to the 2/10. Okay? And then I can simplify that exponent. 2 over 10 is the same as 1 over 5. And then they want you to convert it back into a radical. Okay, so this is the 5th root of x. let's try 86. You have the cube root of xy raised to the 21st power. Okay, so I want to convert it to a rational exponent. So I'll have xy to the third power, and then raised to the 21st. And then we can multiply out exponents. So 21 times 1/3 will end up being 21/3, which is 7. Okay. And then we could use product to power rule to convert this into x to the 7th, y to the 7th. There's no need for a radical on this one. It's a bit weird, but that's kind of, it is what it is at that point, and that's it. So let's look at another one, 98. So we have the 6th root of ab squared times the cube root of a squared b. Okay, so I'm going to convert these to rational exponents. We have ab squared to the 1/6 times a squared b to the 1/3. Okay, I want to kind of distribute my exponents, so I have a to the 1/6, b to the 2/6, which is the same as 1/3, and then a to the 2/3 times b to the 1/3. You can add exponents, so you'll have, in this case, I want to get a common denominator, so 2/3 is the same as 4/6. So I'll have a to the 5/6 times b to the 2/3. I need in order to convert it back into a radical, with both of these guys on the inside, I need to get a common denominator. So this will be a to the 5/6 times b to the 4/6. And then I can put them both under the a 6th root. Okay, so 6th root of a to the 5th, b to the 4th. If that was a little too quick for you, you can always rewrite it as a to the 5th, b to the 4th raised to the 1/6. You see, if you then multiplied it out, you would get back to here. But the 6th root then of a to the 5th, b to the 4th is where I had ended up. So I kind of skipped that little step there. Sorry about that. Okay, let's look at our practice plus type problem, and then we'll just end it. So this is extra. I just want to try to challenge you. You should always try the challenge yourself. A lot of these classes, we kind of just want to get everybody on board, but ultimately, getting everybody on board isn't exactly the most challenging scenario. There's some people that are gonna already be on board, and they're just sitting there kind of, okay, what do I do now? Well, you want to challenge yourself. You want to kind of push yourself a little bit forward, because the next level class may not be kind of this onboarding type class. They may kind of expect everybody to already be on board. So you want to constantly kind of challenge yourself, push yourself a little bit farther, because you don't know what's in the future. Okay? So anyways, this is raised to the -6. I got x to the -5/4, y to the 1/3, x to the -3/4 raised to the -6. Okay? A lot of ways you could do this, and the way I kind of think of it is just go ahead and multiply out the exponents. I mean, you could flip the fraction, change the sign out here, but I don't think it's going to help you in the long run. So let's just multiply out the exponents. So get x to the 5/4 times 6. 6 is the same as 6/1. And then it's 3/2. So 15/2. Negative times negative is positive. So you get positive 15/2. Then y to the 1/3 times -6. It'll be negative. But 1/3 times 6 is 6/3. Put the 6/1. Oops, you can't see that. 1/3 times 6 is the same as 1/3 times 6 over 1. 1 times 6 is 6. 3 times 1 is 3. 6 divided by 3, of course, is 2. Okay. And it's negative in this case. Downstairs, we have 3/4 times 6. Of course, that's the same as 3/4 times 6 over 1. I'm going to factor as I go across. 3 times 3 times 2 all over 2 times 2. The 2's cancel, and I got 9/2. Okay. So downstairs, negative times negative is positive 9/2. Then I have some repeated bases here, so I need to combine these using quotient rule. This has a negative exponent, so I need to move them downstairs. Okay, so to combine these, I subtract their exponents. If I bring this up, so to speak, I have to go this one minus this one. Okay, so it would be 15/2 minus 9/2. And I got to bring this guy down. Okay, so y squared to get the positive exponent. All right, so then I have x to the 15 halves minus 9/2 is going to give me 6/2. Okay. And that's all over y squared. And then finally, 6/2 is the same as 3. And then that's all over y squared. And then I believe that's it. It looks like I have something funny in my notes, but I believe that's the answer. Okay. Okay, so these guys just take practice. You may even want to just work with the book, from a book from the library or something, and just go through a whole bunch of problems and get some practice doing these exponent problems, especially if you didn't do a lot of them in your previous math classes, or if it's been like 10 years since you've seen this. You may need to go back and just play around with it, find some problems in a library book and chug through them. Practice, 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 and don't build your house on, so don't make a castle made of sand. You want to make sure you know how to do this stuff for the future. I assume everybody's going to have to take at least one more class in math that's college level, and you want to be prepared so you don't have to, mess around once you get there. So, anyways, there's that. That's my lecture. See you next time.